So once again, thank you for joining this Capella webinar. I'm Rochet, and we will be your moderator today. Just before we cut the chase, just a few reminders on how this webinar works. Your microphone is muted to avoid background noise, so you won't be able to intervene directly. However, if you have any questions for the speaker, please use the Q&A dedicated windows to send them. Not to confuse with the chat. Yeah, that's a lot of you already discovered, and you can use freely to discuss. So in this way, by using the Q&A window, I can easily identify the question and will ask them for you at the end of the talk. And before anybody asked, yes, the webinar is being recorded and will be made available on the Capella YouTube channel. Now it's my pleasure to welcome and introduce our speaker today. Arnaud is a software developer and architect specialized in modeling technologies. He is actively working on MBSE tooling extensions and add-ons applied to various engineering domains. He has a strong background in formal methods and code generation applied to safety critical systems, and is also a doctor holding a PhD in reliability for systems and software from the National Polytechnic Institute of Toulouse in France. So glad you're with us today, and the floor is yours, Arnaud.
Thank you, Samuel. So I'll just share my screen and we can start. So hello everyone. I'm very happy to be here today to present you the work conducted at Obeo during the last few years on the development of Ecodesign for Capella. So Ecodesign for Capella aims at providing means to assess the environmental impact of your system architecture design using Capella. So first thing first, I will present you the context of this study, the work that led us to this result, and the case study onto which we built the current solution. I will then show the tool itself and try to give you insight on what it can do and what it can't. And finally, I will draw some perspective. So, reducing the environmental impact is one of the great challenges of our century. I provided here some quotes from the 6th assessment report of the IPCC. They say that human activities have caused global warming, and it is the responsibility of human beings to actually do something about it. Actions need to be taken rapidly in order to ensure a livable and sustainable future for all. So engineering and systems, that's why we are here today, as part of technological innovation, need to play a role in this endeavor. It is a fact that engineering and systems are a part of the problem, and as they may cause greater environmental impacts, social inequalities, and rebound effects, among others. But with appropriate effort, it may also be part of the solution. You may all be aware that in addition to this, there is a real demand by consumers for such a reduction of environmental impacts, and that market stands to it. In addition to this, institutions may enforce it in the future if it's not already the case. So the question is how to reduce environmental impacts. Means to do it are legion, and we will only focus on today on means to measure the actual environmental impact of system designed using Capella. One of these means is life cycle assessment. So life cycle assessment is a standardized method and the associated tool that allow to quantify the environmental performance of a system. Conducting a life cycle assessment means conducting an analysis of the system environmental impacts. These impacts are drawn from the complete life cycle of the system. So the analysis may itself not take into account the whole life cycle of the system, but it may. The life cycle of the system itself starts from the raw material extraction and goes to the disposal or the recycling of the system, and goes through production, manufacturing of the system, the transportation of the system itself, its use, its maintenance, and all the other phases of its life cycle. Conducting life cycle assessment means identifying and characterizing the inputs and the outputs that are necessary during all the phases of this life cycle. So the inputs may be materials necessary in order to build the system, energy necessary to build the system or use it, the outputs produced during the use of the system, during the recycling of the system, the transportation, the waste, air emissions, or many other kind of elements. Once these elements are identified and characterized and quantified also, you may be able, using life cycle assessment methods, you can compute indicators that will actually give you a quantification of the environmental performance of the system. While assessing this environmental performance on parts of a system, the whole system, on some of the phases of the life cycle, you may have first information, quantified information on what is the performance of the system. But when you are doing again the analysis on a variant of the system or another version of your system, then you can witness the fact that the environmental performance will change, and the impacts may be transferred from one life cycle phase to another, from one indicator to another, and this method and the associated tool will allow you to witness this information, which is really important into the quantification of this environmental performance of your system. So I told you that this method and tools are standardized. So the method is standardized in the ISO 14040 and 14044. So there are 4 activities in this life cycle assessment framework. The first one is the goal and scope definition. So the definition of what is analyzed, what is the scope of the system that is analyzed, what is the scope of the life cycle that is taken into account during the analysis. Then the second step is the inventory analysis. So inventory is the definition of all the inputs, outputs, and the processes that are taken into account during the life cycle of the system. So processes are activities that transform input into output. Then, when this inventory is done, it's possible to use method to compute indicators. And during these 3 phases, the interpretation phase takes place, and the life cycle analyst is conducting this life cycle assessment, is interpreting the data, ensuring their quality, and ensuring the correctness of the analysis that is done. All the elements that are used into a life cycle assessment tool and into the life cycle assessment framework, all these elements, this data, the flows, the processes, the methods, and the indicators, they are all stored in reference life cycle assessment database that are built on scientifically relevant data. conducting a life cycle assessment produce one of the outputs of this this life cycle assessment is a report that synthesizes the information from the computation of the indicators, and one part of this information may be formalized using this kind of data. So I give you here some of the indicators used in some methods. There are many methods, many indicators that can be used. The indicators have various units, so you can see here some of them that are well known, like climate change or ozone depletion, but some others that may not be that easy to understand, but they are all computed. And at the end, it is possible, using life cycle assessment data, to quantify the impact of parts of the system and the positive or negative impact of some part of the system on each of these indicators. So, for example, here you have a simple system made of 5 parts, and for example, the plastic valorization part has an impact on each one of the indicators here, and it has a negative impact on the graph, but it's a positive impact for the environment because it prevents pollution, or it prevents impact on climate change here. So for each one, you can have this kind of information. And this allows you to have a quantification of the value. So what about complex systems? So conducting a life cycle assessment on complex system is obviously a complex task because of the complexity of the system. So first, being able to scope what needs to be analyzed in the system. So being able to conduct early analysis on the system, being able to conduct detailed analysis on the overall system, being able to focus on some part of a system is something that can be complex on very complex systems. And it is complex also because of the nature of complex system, which is composed of many components, many relations. It has many data sources. The variety of data is very complex. And this complex structure leads to also emergent properties that will also complete this complexity. And then on complex systems are meant to evolve during the design and maybe after also. So evolution of complex system also mean that you will need to be able to keep synchronized life cycle assessment and system analysis with your system data and system specification, which may be very complex on complex systems. So the usual solution for complex systems is model-based system engineering, at least the solution that we advocate usually into the Capella Webinar. So the complex systems, so using model-based system engineering will provide a whole spectrum view of your system. So from the early steps of system development and system business need perspective, for example, and then up to the physical implementation of your system, or physical specification of your system, maybe. An MBSE model is a formatted, formal way, a formal model of a system, and it's a coherent logical decomposition of a system. So it allows you to have something coherent, a model that is computational, meaning that you will be able to compute actually information on it, and it's also integrated into a tool that helps you manage the complexity of the system. And then the question that lies behind will be, why not use an MBSE model as a reference to automatically generate a life cycle inventory in order to be able to conduct a life cycle assessment of the system and of its environmental performance. So this would be an iterative and pragmatic approach in order to conduct life cycle assessment on complex systems. So this is what we advocate for Ecodesign for Capella, in order to answer the need for solutions to measure and reduce environmental impacts of systems. So the approach would be to combine life cycle assessment, as I presented to you previously, with model-based system engineering in order to form an eco-design process. So the eco-design, it's the integration of environmental aspects, into the development process of a product. So it's about taking into account environmental performance of a system during its development, and not only assessing it when the system is developed. So, about integrating Capella and life cycle assessment software. So, on one side, you have system engineers that will manipulate Capella software and produce a system, a Capella model of their system. And on the other side, the specialists of life cycle assessment, which are eco-design engineers or life cycle analysts. They produce a life cycle analysis. They will produce life cycle analysis based on the model-based system engineering Capella model completed with dedicated information. And by ensuring a numeric continuity between those approaches and tools, will allow the complex system architect to evaluate the impact of their design choices onto the environmental performance of the system. And the numeric continuity ensure more faster and more frequent assessment of these environmental impacts. So this is what we aim for. So at the beginning, there was a first experiment back in 2019, and the first prototype. So a collaboration between Monta Innovation, Obeo, and formerly Altran, that is now Capgemini Engineering. So we worked on the first prototype integration of Capella and lifecycle assessment, first connection between the tools, first integration into Capella, and some first thought on the methodology that should be applied between the tools and each actors that actually use these tools. Back in 2020, we have already done a Capella Day on this subject. I leave you the link here, so you can you can have a look at it. In these days, the case study was a part of a boat yet to be built. That is the Monta. So this part of the boat was the waste to electricity conversion unit, and this unit was basically a small factory taking as input plastic taken from the ocean and transformed into electricity and byproducts. The study lied on this subject, on this system, and was more in order to find what needed to be done in order to conduct such analysis using a model-based system engineering approach. Then, after this experiment, we launched a project, a research project called Ecoplex, which lasted 18 months between and finished in 2023, in January 2023. So the aim of the project was to allow complex system architects to assess faster and earlier the environmental impact of their design choices. So really the scope of the Ecodesign for Capella tool. At Obeo, we were in charge of the development of the software. We led the project. And in the project, we were with Capgemini Engineering, the LS Design, Sterling Design International, Finor Cleaner, and Mountain Innovation. The project gathered system engineers, chip builders, and life cycle assessment specialists, and also software developers, in order to produce a solution and also to work on the associated methodology in order to conduct the life cycle assessments. So we worked on 2 case studies provided by the naval architect partners. And this work led to the production of this tool, Ecodesign for Capella. Sorry. So this Ecodesign for Capella, so first it's an extension to Capella that allows to initialize life cycle analysis into a tool called OpenLCA, based on the Capella model. So first you graphically model the system to be analyzed. So you model your system using Capella. Then you can extend it using Ecodesign for Capella in order to set life cycle data such as lifetime for components, exploitation profiles, consumptions, emissions, materials that are used, and you can quantify all this information directly into your Capella model. The information that are attached into the Capella model are based on reference lifecycle data, which are the same as the one used by the lifecycle assessment tools. Then from both of these data, the Capella model and the Ecodesign for Capella extension data, you automatically initialize a lifecycle analysis in a format called ILCD. This file format is then taken by the lifecycle analysis tool, which can then compute, interpret, and produce the lifecycle assessment report. Additional analysis can also be done directly from this initialization of the lifecycle inventory directly into the lifecycle assessment tool. What are these lifecycle assessment tools? So today we work mainly, or we work only with OpenLCA through the Zolka and ILCD formats. But in the future, we may also work with some other tools like SimaPro or Ecodesign Studio. SimaPro, which is the leading tool in the lifecycle assessment market. But why? So all these tools allow to conduct detailed lifecycle analysis, and they rely on scientifically relevant databases. Why do we work with OpenLCA? Because it's a free and open source tool, which is Eclipse based. And so it was the perfect target for experimentation within the Capella ecosystem. The OpenLCA tool is developed by Green Data in Germany. We also during the experiment in the Ecodesign in the Ecoplex project, we developed also a small web access to allow non-Capella experts to access the content of the Capella model, and especially to access the Ecodesign for Capella data attached to elements of a Capella model. And it allows them to witness the data, to see it and manipulate it, and to edit the data from this web view. So this web view is a collaborative edition of the Capella model content, which is served through a web server and through the Team for Capella solution. So it's really an experiment on how to collaboratively edit Capella model content directly from a web view. So this was done during the research project. So this research project was on 2 case studies. We relied on these. So 2 ships, sorry. The first one was the Mobile 8, so a waste removal ship provided by Monta Innovation and Effinor Sea Cleaner. The idea was here to define improvements that can be done on the design and the operation of the ship based on the analysis that can be conducted using the tool in order to make the ship more eco-responsible. The second analysis was on the crew transfer vessel provided by SDE and PRU. And the idea was to evaluate the impacts of an existing ship and to study eco-design variants. During the project, we also conducted some validation of the tooling. So we applied one method to both of the use cases. So from a textual specification of the use cases, we lifecycle analyst made a lifecycle assessment of the system. So they directly use this data to conduct a lifecycle assessment. And on the other side, on the system engineering side, Capella users were able to model the system using Capella, attach additional data, and then automatically produce a model usable in OpenLCA. Then lifecycle analysts are able to compare both models. So the result was that for both systems, the results were equivalent. So it was a real success for us to be able to have equivalent analysis. So now I will go into the tool and provide you with some insight. So first, you can see here a component, a Capella component, generic ship with some propulsion. We will use another example in the video, but whatever. For one component, with the Ecodesign for Capella add-on, we attach a state machine. So a state machine that is dedicated to model the life cycle of the system. So you see here production, distribution, operation, end of life, and maintenance. That are the 5 steps, the 5 default steps of the state machine. And then inside these states of the life cycle, into these life cycle phases, we can attach life cycle assessment data. For each data, as seen here, you can say the quantity, the span, and then you will get some computation of the actual values that in the context where they are added. So let me just. So here you see first another example. So it's a simple car. So this model is just a car. We have done a physical analysis of the car. So we have a car system with some subcomponents, and we will try to conduct an LCA analysis on this system. So first, we need to have some life cycle assessment data. So we will be able to import life cycle assessment data into an element called an inventory that will contain the flows, the processes, and the units used into all these elements. You see here that we have a view of the system. It was a physical architecture blank model of the system. We have added a small layer on it in order to show where life cycle data are attached. This is just a small view in order to see. What is more important is this property view, the dedicated property view here that is developed especially in order to be able to attach data into the Capella model. So you see here that for the production of the car, we need some electricity. We are in France, so it's electricity from nuclear. We need 2.82 megawatt hour of electricity to produce one car. We can select the units. Actually, there is a set of units that comes with the life cycle assessment data. You can see here that we assume the car to have an exploitation quantity of 250,000 kilometers, so it will live for this amount of kilometers. Then we can go to the wheels. When we are on the wheels, we see that we need some aluminium in order to produce the wheels, and we need to recycle this aluminium at the end of life of the wheels. And then we have some tires. So tires have a lifetime that is 50,000 kilometers. And for the maintenance of the tires, we need some compressed air every 10,000 kilometers. Okay. Then we go on to the gasoline consumption of the car. So we have two different processes here. One for urban consumption, another for extra urban consumption. This is really simplified. And these processes gather the impacts of burning actually gasoline for 1 kilometer of driving with your car. But this was located into the consumption subcomponent, a behavioral component. Now we specify that in the car component of the system itself, we specify that the car will be in a urban consumption for 65% of its lifetime, meaning that it will spend 162,500 kilometers into this urban consumption, and it will consume this amount of kilometers of gasoil. You just see that here there is some live calculations that are done. Okay, so you can attach actually LCA data. So you see that you have the inventory, so the data that has been imported previously. You can select some data, and then put the quantities that are the one that you want, and allocate the data to the state and the life cycle phase that you want it to be added to. Okay. Perfect. So you see that we have added something into the solution. So it was a mess, so we delete it. Okay. So good. Then you can export the data. So from this point, you have a model and you can export. You can either select to export from the component itself, so the car component, for example, or from a life cycle phase directly, and only export the data from the life cycle phase. So once this is done, then you can go into the OpenLCA tool and import your data. So into this tool, you have also the life cycle assessment data that are from a specific database. And then you get all these elements that are created by the Ecodesign for Capella tool. All these elements are processes. So we are in the life cycle assessment world. And these processes reference the actual content that we have added into the Capella model. So we have produced processes for every couple of component of the system and the stage of its life cycle. So there is a lot of processes that are generated, but it actually covers all the elements that are inside the system model. So you get here a model of your system into a lifecycle assessment tool. And the elements and the structure of the model is the same. So here I launched a small analysis using an impact assessment method called environmental footprint, EF. Okay. And then the analysis is done. Okay. And we get some information on the various impacts that our system has based on the impact categories. So here, for example, what we can see directly from this analysis is that 98% of the impact on the climate change is because of the car operation, so the gasoline consumption, which was nearly obvious, but now we have some data to assess it. If we go to on the ozone depletion impact, then it's more on the production of the system and the use of steel. So our Capella extension, this Capella extension allows you to attach life cycle inventory data, so LCI data here, onto your Capella elements. So it's an extension of components that allow you to allocate these data onto explicit lifecycle phases. So a representation that we can have is that for each component we have the ability to attach data and to quantify the lifespan of the component. This lifespan may be time, maybe using some other units like length, for example, for the car, or 25 years for a boat or a ship or something like that. So in a hierarchical context of a model, of a Capella model, you have one component, sub-components, and every component have its own life cycle inventory data, and its lifespan. So you see that we can have something like this. So for example, C1 is a car with a lifespan of 250,000 kilometers, and C11 is a tire with a lifespan of 50,000 kilometers. What it actually means is that the tool will do the projection on the model. It will actually not create all these elements, it's just computed. And it will automatically project to cover the whole system use. So specifying this data means that we will take into account the impact for 5 times the tire here. Or in this model, 3 times C11 and 2 times this one. Based on this, then you have a complete model of your system and all the impacts that your system will have. Then you want to export this data into a lifecycle assessment tool. So what you can do is either do a global export of the whole model in order to do a global quantification of the impact of your system. But you may also be able to do an export of only a sub-part of your system, a sub-component, or a sub-tree of your system, in order to do some local quantification, maybe some optimization of your part of your system. But you may also be able to do an export using a second dimension that is a life cycle phase, and select the life cycle phase that you want to have in order to do your analysis. Then in the life cycle assessment tool, you get a model that keeps this structure, so you will be able to, if you export everything, then you will be able, if you want to conduct a partial analysis of your system, even in the life cycle assessment model. So, what is the current status of Ecodesign for Capella? Is that we have this tool, we have the extension to Capella, the ability to reference external life cycle assessment data, and the ability to export data to a life cycle assessment tool. Then, what we expect to do, what we would be able to do in the future, would be to probably connect to other data sources. There are many data sources, many formats. There are online data sources also that are available, so it may be interesting to have additional data in order to directly query the data from the outside. We would like to add some enhanced modeling capabilities, the ability to express quantities using formulas, insert parameters into the Capella model, and then being able to reference parameters into formulas in order to have something way more complex. Probably being able to reference quantities on other data, so we have dependent values into the Capella model. We would like also to use the actual Capella model extended with Ecodesign information as a way to formalize the analysis that will be conducted using a lifecycle assessment tool. So, kind of defining the meta analysis parameters, the meta parameters for the analysis, and it's called the functional unit in a life cycle assessment tool. Another addition would be to actually take the data produced by the life cycle assessment tool and feed them back into the Capella model in order to conduct value analysis on the Capella model, and actually gather this information onto the model and take them into account into when doing some comparison of various versions of a system, and take them at the same time as weights or prices or performances, for example, of your system. So lifecycle assessment data as first level information for trade-off of your system. We would to improve the technical synchronization between both worlds in order to, for example, ensure data consistency, update data on both sides based on modification, share hypotheses, because hypotheses are done and they may need to be shared in order to for the other party to understand the choice that are done. We also would like to provide additional export formats in order to discuss with additional tools. We choose to export the data into the lifecycle assessment tool using a specific format, the LCA format, and the data is formatted in a way that you find the structure of your Capella model into the lifecycle assessment tool. This may not be the best way for lifecycle assessment. Maybe different format may need to be applied, so it may be modified too. We would like also to allow reuse of the model that is produced in order to complete the data into the lifecycle assessment tool, which is actually the case. It's possible, but it will require additional work. And at the end, we would like to produce an industry-ready version during 2024. it may be a target that we will see in the future. So finally, we are launching the Ecodesign for Capella Early Adopters program. So the Ecodesign for Capella tool is still in an experimentation phase. We are searching for partners to provide feedbacks on the tool, to experiment on other case studies, maybe in different domains, to participate in specifying the new functionalities. I have drawn some of the functionalities that we may add, but there may be others. So we have put online the Ecodesign for Capella webpage. So, and you can find all the information about this early adopters program online. Thank you for your attention, and if you have questions.
Yes, we do. a lot of questions, actually. Thanks, Arnaud, for those insights. Quite interesting. And I'm pretty exciting to see who we'll have in this early adopters program. Okay, let me just share the questions we have. Which environmental database can be used as a life cycle inventory?
So we support the Zolka database format. So we rely actually on the OpenLCA API to import data. So we are able to import Zolka file formats. There are many databases that provide version of their databases using this format. It's also possible using OpenLCA to actually convert data from external data source to Zolka file format. So we actually support, we did some experiment with the basic one, ELCD environmental database. We did experiment with the Eco-Event database too. And I think that's it.
Okay, thanks for that. Next question. Validation tests shown equivalent results. Was there any difference on the lead time?
On the lead time, the time necessary in order to conduct the analysis? Not sure to totally understand the lead time.
Yeah, maybe.
If it's the time necessary to conduct the analysis, then we did not assess this. This experiment was done during the project, so there is. We have no feedback on the time necessary to.
Okay, and can I confirm it was this this time?
Okay, so no, there is no assessment of this. Actually, it's very difficult to to assess this difference, but good question. We may look at it.
Okay, next one. Is this extension open source?
So it's not open source. It's so that's why we opened an early adopters program in order to get people to try it. But it's not open source for now. It's free if you if we agree on the fact that you can give us feedback on the tool. But it's not open source now. There is actually, we don't know how it will be in the future.
Yeah, we'll think about it. And
yeah.
We are keeping all options available today. Next one. So is the tool accessible to be used? Yes, through the early adopter program. And can the tool also account for circularity or component reuse?
So the answer for this is yes, because if you create a Capella model of your system or of a component, then you conduct your LCA analysis of this component. You will get a process gathering in the LCA world, you will get a process gathering all the information for your system. And this process can be exported into a Zolka database that can be imported back into Capella. And so one of your other system will be just a process into the higher level Capella model. So you will be able to reuse and reintegrate the impact of another system into a system. So there are means to do it. It's not the more efficient way to do it. There are maybe some tooling to do around it, but yes, it's possible.
Okay, next question. What about the carbon footprint of the supply chain?
So the carbon footprint of the supply chain, so the environmental impacts of the supply chain. So either you use life cycle data that include the carbon footprint or the environmental impact of the supply chain, so you get it. If not, you can also model the supply chain. So your system may be a plane, for example, but you may also have a system of the supply chain of your plane. So it will include part of the supply chain of the plane. And if you model this correctly, then you will probably get the carbon footprint of the supply chain of your supply chain. So yeah, basically you can do it, but some LCA data includes already this data, some not. So you have to choose wisely, and that's the work of the life cycle assessment analyst.
And last question from Mozilde. Can we customize the state machine?
So for now, no. It's not possible to customize it, but there is no technical difficulties to do it. It's basically possible to do it. But it needs some adaptation. And it's probably one of the perspectives that I should have drawn also. Thank you.
Thanks, Arnaud. Well, you partially answered this one, but just to be sure, any possibility to connect to GaBi or SimaPro?
So not yet directly. It's not possible directly. If you can export your data from GaBi or SimaPro to a format that may be suitable into OpenLCA, or that can be used to connect to Capella, then yes, but there is some work to be done in order to do this.
Thanks for that. The proposed solution enables quantification, but what about the product optimization?
So conducting an optimization will require to be able to compare actually the analysis. So this is one of the difficult parts. You can conduct an analysis. So you export your model, you conduct an analysis, then you modify your model, and then you re-export it. So there are some technical difficulties that make it not possible right now to import both versions of the system into the OpenLCA software. It's just technicalities, but it's a limitation for now. But based on this, if you can import both of the version of the system, then you can assess which one is better for which case and locally do some optimizations. But it will also require it may also be done through the feedback approach. So you take the result of the analysis, then you feed it back to Capella, and you do some value analysis for optimization. But this, again, needs to be developed.
Okay, yes, thanks for that. So this one is pretty interesting. I don't understand why the analysis of the life cycle is important at the design phase.
So, because it's at the design phase that you do some choices on your system that you will not be able to change afterward. So the earlier you do this analysis, the earlier you are aware of the environmental impacts of your system. So if you actually start to quantify, even at the course level, your impact of your system at the design phase, at the early design phase, the earlier the better, and the bigger the impact will be avoided or handled, let's say.
This one is interesting too. Did the system engineer and the LCA expert work on the same functional structure?
Material energy flows of the system. Yes, actually the specification was the same. We all started from the same specification, which was partly Excel content and partly more libre, more free content, let's say. But they work on the same structure, the same data, input data, but the resulting LCA model were completely different, really completely different. The one produced from Capella was highly structured, and the one developed using directly in OpenLCA was free. Basically, for each project, the shape of the model was completely different. So the structure, the resulting structure was completely different.
Okay, thanks, Arnaud. And what is your position regarding PLMs trying also to calculate LCA?
So I am not an expert at all into what PLMs can actually do. I know that they try to also do some things like that. So I think in order to get a real answer to this question, we can probably answer question afterwards also. Samuel, I don't know, I think we can post answers afterward.
Well, we won't have time to address all the questions during this webinar, definitely. So probably we will answer all of them on the Capella forum or something like that, yeah. or provide them on as a message to attendees anyway. So, well, you can take some time to think about it and provide an answer later. Okay, maybe. Okay, a last one. Can this system be applied to the evaluation of environmental impact of flows?
I would say why not? Actually, a government or even a country is a system. So yeah, why not? We may be able to model laws or a country, and then being able to conduct a life cycle assessment of this. I know there are some northern countries that actually have computable models for their countries, and they actually do these kind of things.
Okay, thanks. So as I mentioned, we still have a bunch of questions, but unfortunately we are running out of time, so we have to conclude. And well, anyway, we keep you updated on what we will do with an unanswered question, and you will receive an answer. So let me just go to the slides and go to the conclusion. Thanks again. Anyway, Arnaud.
Thank you.
Yes, I will just conclude. Once again, thanks for the presentations. Thanks for all those answers. Thanks for attending this webinar. It was a pleasure to share this moment with you. And have a good day and goodbye.